CLI and a cross-platform IDE for C and C++. Download now.
Hello, everybody. Welcome to my talk. My name is Timur Doumler. My talk today is called Contracts for C++. And I got the title slide up here. And the most important aspect of this title slide is that it has a version number. It says version 2.0 there. And the reason is that I actually gave this talk quite a few times before, eight times to be precise. This is the 9th iteration of this talk. I actually have this time rewritten a lot of the talk, so it's actually quite different from those earlier versions. So don't watch those. The reason is that this feature that I'm going to be talking about has now actually been approved for C++26 as of very recently. So this is the first time I'm giving this talk after it's actually now part of C++26. That was one of the reasons why I reworked this talk quite a lot, as you will see. All right, so this is good. This is now a part of C++26 contracts, a new feature. My next slide, the previous versions of this talk was the proposal. Here's what we propose, but I don't have to do that anymore because now it's part of C++26. So now instead I can show a screenshot of CPP reference because it's already on there, right? And I lied to you, the feature is not actually called contracts, it's called contract assertions. It's an important difference, those are two different things. We're going to talk about that later. So the feature I'm going to be talking about is a new feature for C++26 called contract assertions. It is already, as I already said, on CPP reference. They didn't quite get that right. The example code here at the bottom doesn't actually compile. I think they'll figure it out. I think after you've watched this talk, you will know what's wrong with this code and why it doesn't compile. You can also play around with it already because we got 2 implementations. One in GCC, one in Clang that are working today. They are on Compiler Explorer today, thanks to Matt Gottbold. Thank you, Matt. You can follow the links here because you need like some special flags to make it work because they're obviously not part of the standard yet because C++26 is not actually out yet. So if you follow these QR codes, you're going to get to a Compiler Explorer instance that has all the right flags set up, so you can start playing around with it. If you don't want to scan the QR codes, you can go to this paper, P3460, scroll down to the last page, and that's also going to have those links. I'm going to have quite a few of these paper numbers in this talk, P something something. Those are committee papers. You can find any such paper on the internet by typing in your browser wg21.link/paper number. So this is how you find any of those papers that I will be referring to in this talk. Okay, so what I'm going to do before doing anything else is give you a short introduction of what contract assertions actually are, how to use them. That's kind of a thing that I'm doing this time around. I'm not starting with theory. I'm starting with, and here's what it is. And hopefully that's going to be a little bit more approachable. So fundamentally, contract assertions are a better replacement for the good old assert macro. That's what they are in one sentence, right? So if you got C assert today, right, you can do that today. You can write an assertion. You have to include the C assert header, and then it's a macro. So with C++26, you don't do that anymore. Instead, you write contract assert. Obviously, we couldn't reuse the assert keyword as a keyword because it would then clash with the macro. We can't really do that, so we had to find a new keyword. Took a long time to agree on one. This is the one we picked. It's called contract assert. It kind of works in the same way, except you don't have to include a header anymore. And it's also a proper keyword now, so it's not a macro, which solves a lot of problems because you don't have to deal with macros anymore. But it actually has the same default behavior. So if you write this code on the right and without any extra flags, if you just compile that on the command line, it's going to do the same as the code on the left, which is it will check the so-called predicate, the Boolean expression that you put into the assertion. And if that predicate is false, it's going to print a diagnostic to the standard error saying, assertion failed, and then terminate your program. So that's what it's going to do by default. But the kind of salient feature of assertions in general and contract assertions specifically is that you can turn them off. With the assert macro, you can turn it off by defining ndebug, either in the code by #define, or more commonly as a build option like -d ndebug or whatever your compiler flag syntax for that is. Contract assert is not a macro, so you don't use another macro to turn it off. Instead, it's implementation defined how you turn it on or off, because we don't standardize things like build flags in the standard. But in practice, in GCC and Clang, there is a flag like this: f contract semantic equals ignore, and that's going to turn your assertions off. Right. So I think that's very easy and simple. Right. If anything is not clear, feel free to interrupt me, raise your hand. And we'll talk about that. But I think pretty easy so far. This thing ignore is called an evaluation semantic. So that's another term we have now in the standard, an evaluation semantic. Each assertion is evaluated with a semantic. And the assert macro has two options, like ndebug on or off. Contract assert has 4 options for which semantic you might be using. We got ignore, observe, enforce, and quick enforce. And enforce is the default, but you got these 3 other options as well. You can specify them in whichever way your compiler decides to give you that option, typically as a compiler flag. Ignore is the one where nothing happens, the assertion is just ignored, as the name says, and you use that when you just cannot or don't want to afford the runtime cost of the check. So you don't want to actually check anything, you still want the assertion to be there in the code, but you don't want it to actually do anything. So that's when you use ignore. Enforce, which is the default, is what we saw in the very beginning, is when you need the safety that you get from the check, so you can't move past the check. You will know when the check fails, but you also need this convenient diagnostic information. You want to have some kind of like nice output that tells you, you know, this in this line, this assertion was like failed. Then there's observe, which checks the predicate, and if it falls, it does also print the diagnostic, but then it just keeps going, which then might still crash your program. And you ask yourself, why do we need this? This seems not as safe. But turns out you really, really need this. You can't really deploy assertions without it, in particular if you have a pre-existing legacy code base and you want to add new assertions to it. And there are cases where either you're not sure if your assertions are actually correct, and you don't want to crash your production system if they're not, or maybe you want to know if there is a bug, but you already know that your production system has been running without issues for the last 10 years. So, you know, if there is a bug, it is benign for some definition of benign, and you also don't want to crash the production system. You just want to know, you know, if the bug is there, and then later, when you're reasonably confident that you fixed the bug, then you can turn the enforcement on. But initially, you want to just observe the assertion. So that's what this semantic is for, very important for deployment and legacy code bases. And the last one is quick enforce, which is similar to enforce, except it doesn't print a diagnostic, it doesn't do anything at all, it just checks the predicate, and when it's false, it terminates your app immediately. So it can do something like a trap, which is like one instruction. It doesn't call into any other code, it just gets you out of there as quickly as possible. And that is an important option when, for example, when you want maximum safety, when you don't want to give an attacker, for example, any surface to like try and take over your app if something went wrong, you just immediately terminate, get out of there. And also that's minimum overhead. You still have the check, but there's no overhead on it beyond the check itself, right? So that is also a very, very important semantic. So you get all 4 options with contract assertions in uses 26, and all of those 4 have important use cases. Those 3 semantics, observe, enforce, and quick enforce, are called checking semantics because they are checking the predicate. And the last 2, enforce and quick enforce, are called terminating semantics because if the predicate fails, they terminate your app. And one more thing is, by default, they print a diagnostic. That's the recommended default behavior. But that's actually configurable. And that's another thing you cannot do with the cassert macro. And that's another reason why people today don't use cassert macro often, but they use their own custom assertion macros. Because maybe you want to do something else than just the default diagnostic that you get by default. So with contract assertions, you can actually configure this behavior. So the default contract violation handler, which is how we call it, will print a diagnostic. But you can also install your own user-defined contract violation handler. And you use that.
A quick question.
There's a quick question.
Yeah, the message, can you customize the message, the content itself?
You cannot customize the message. If if you don't install your own violation handler, which is what we're going to get to in a minute, then you're going to get whatever behavior you get like from the compiler. Whatever the compiler decides to print, that's what you get. But yes, you can customize that behavior by installing a user-defined contact violation handler. And you use that by defining a function with this signature. It's got to have exactly this name. It's got to be in a global namespace, and it's going to like take one parameter, which is a const reference to a contact violation object. And so you define that function. In some translation unit, you link it in. So it's a link time thing. It works exactly the same as operator new, operator delete. If you want to replace those with your custom global operator new and operator delete, it's the same mechanism. It's called replaceable function. Essentially, it's a weak symbol. So you kind of link it in, and at link time, it's going to replace the default with your own implementation. And your own implementation, it's going to get called whenever you have a contract violation, whenever one of those predicates is false, and you are using the observe or enforce semantic. And in there, you can do whatever you want. You can use your own logging in whatever format you want. You can set a breakpoint. That's another feature we got in CPLUS 26. Or you can wait until the user attaches a debugger and then set a breakpoint. You can print a stack trace. You can print the stack trace minus the last stack frame, which is the contact violation handler itself. That's another really cool feature. You can also print the stack trace and then defer to the default contact violation handler, which is going to print the message. And you can do this deferral by calling this very long function, invoke default contact violation handler, which does what it says on the tin. And you can do anything you want in there. You can also throw an exception. That's very interesting. So that what that's going to do, it's going to unwind the stack. So in this way, you can handle a bug in a way that doesn't terminate the app and doesn't keep going, but instead, unwinds the state to somewhere else where you can maybe handle this. This is maybe a bit unusual, but you can do it. It does require you to follow what we call the Lakos rule, which is if your function has a precondition, if there might be conditions under which calling the function is a bug and it's going to violate an assertion, don't put no except on it, because otherwise that exception you're throwing here is going to slam into that no except and terminate your application, which is exactly what you don't want when you're doing this. So the C++ standard itself largely follows the rule, like vector operator square bracket, for example, does not have no except on it, although the actual implementations often do. That's a choice they can make. That's another topic I'm not going to talk about. Long discussion. More importantly, you have this parameter here that you get passed into your violation handler, which is this contact violation object. And that is something that the implementation provides for you, and that contains a bunch of information about the assertion that has been violated. So there's a little bit of standard library API behind this that is now also part of CPLUS 26. It's all in this header contract, so that's a new header. You don't have to include that to use contact assertions. You only have to include that if you actually want to implement your own violation handler, which is like one person per company, I guess, does that once. So that's not something you use very often, but if you do, it has that stuff in it, not much, very lightweight API. Basically, it's just this class, contract violation, which is the thing that you get passed in. It has a bunch of member functions. Note that it doesn't have kind of data members that are prescribed here. So we want it to be ABI forward compatible. So you access it by these functions. Comment gives you a human readable description of what went wrong, typically containing the expression that was violated. Detection mode tells you what went wrong kind of procedurally. Either you got a predicate that evaluated to false, or you got an exception that was thrown while you were checking the predicate. That's the other thing that will land you in this contact violation handler. And if you got an exception, then you also get an exception pointer to that exception, so you can rethrow it, handle it, do something with it. It's very important to distinguish those two cases, though. So if you get an exception thrown while you're checking the assertion, while you're evaluating the predicate, then you get this exception pointer and you land in the contact violation handler. If then the contact violation handler itself throws an exception, that's a different exception, and that's just going to unwind the stack. So two different cases. And then we got this kind method, which we will talk about in a minute. We got location, which tells you where the assertion is. It's going to give you a source location. We got semantic, that's going to tell you the evaluation semantics, so enforce or observe. And it's going to tell you whether that's a terminating semantic, right? That's another term we discussed in the beginning. And then the last bit of library API here is that you got this function that we already discussed, which is the freestanding function to call the default violation handler. So that's what you get. That's what we have right now. This one here, I mentioned I wanted to get back to. Turns out there's actually 3 kinds of contract assertions. That's the other really, really important part of this feature. We don't have just contract assert. We actually got 3 kinds. You got pre and post and contract assert. So contract assert we already talked about. It's called an assertion statement, but we also got pre and post. So that's called a precondition assertion and a postcondition assertion. And together, those 2 are called function contract assertions because they go on function declarations. And all 3 together are just called contract assertions. So that's kind of the nomenclature we have here. Hopefully that's not too confusing. That's kind of what we ended up with after long discussions on the committee. So let's talk about these 2 because they're like really new and really cool, like pre and post, the function contract assertions. So they go, as I already said, on function declarations. So if you have a function declaration, you can put these pre and post assertions directly on there. And they work exactly as contract assert, except that they're on the declaration and not in a body. And you can express pre and post conditions with it. So for example, and pre is called when is checked when the function is called. So you can, for example, when that function is called, assert that the pointer you passed in is not null and that the index you passed in is not negative, whatever you want to check there. And then when the function returns, those post-condition assertions get checked. And then you can check whether the widget you're returning, that's kind of a contrived example, but like is valid and the index of the widget passes, like it has the index that you passed in or whatever. So the other really new thing here is, so the main new thing is that they're actually part of the function declaration, as I already said. But that's really important because unlike assert, you can put that in a shared header and you don't need to see the implementation of the function in order to see those assertions, which means that humans and compilers and IDEs and static analysis tools and everybody else sees those assertions without having to look or know or have access to the function implementation, which might be in a different translation unit that you don't even have access to, right? So that makes these assertions a lot more visible, a lot more useful. Your IDE can display a little blob saying, hey, this function has a contract assertion. You probably might want to make sure that you don't violate that precondition, right? And your static analysis tool can do that. The compiler can insert the checks right there. And then the other new thing is that the post condition here, you can directly refer to the returned object, like the object that the function is going to return. And you can't really do that with macros today because that also works with return value optimization. It works with guaranteed copy elision. Like it just works. It just refers directly to the object that you're going to be returning. And you can give it any name. I just chose W here. You can choose R or ret or X or whatever. And then you write colon, and then you can use that identifier to refer directly to the object that the function actually returns. Not a copy, not a reference, the actual object. And that is pretty much it. That's how this feature works. That's what we added to CSS 26. That's kind of all you need to know to get started, really. There are, of course, a few more details. I'm going to talk about some of those in the remainder of this talk. But those are mostly things that if you get them wrong, you'll find out because the compiler is going to bark at you or you're going to notice that the thing that's happening is not the thing that you thought would happen. So kind of you can discover those little details kind of as you go. But like this is the main thing you need to know. This is kind of the scope of the feature and how to use it. Are there any questions about that so far? There's 2. I do have a lot of slides, so let's not spend too much time on this, but if they're quick, we can deal with them now.
Yeah, the pre and post conditions, are they required to be side effect free so I can't modify the return
We're going to
value?
talk about side effects later. Okay. Next question. Big topic, important.
If you're setting it to ignore for the...
Sorry, speak in the mic, please.
Sorry, if you're setting the condition flag to ignore,
yeah,
does that mean it's going to swallow any exception thrown and with the default implementation?
If you set it to ignore, then nothing happens.
If the assertion throws a...
the assertion will never get checked.
Oh, okay. So,
Like
yeah,
the expression in there will never get evaluated. It's like you put it in a size of and then you never use the result of that size of. It's still going to be parsed and ODR used. Unlike with the macro, the macro just throws out all the tokens. That's bad. We don't do that. We still parse it. So it has to be in valid expression, but we never evaluate it if it's ignored. It just has to be syntactically valid, but it never nothing runs. No instructions are added. It's as if it was not there.
The post condition is running on the callee or in the function.
We will get to that.
Okay.
All right. So where are we now with this? So obviously C++26 is not yet the new official international standard. There is a roadmap for this, which is kind of our usual 3-year cycle on the C++ standard committee. So we got kind of 3 meetings per year. So we got 9 meetings in total to finalize C++26. We are now here. So we are past the design freeze for C++26. There's one more meeting in Sofia in June where wording can still be added. So this is where reflection is. The reflection has been design approved, but the wording is not in the C++26 draft yet. But for contracts, the wording is already in there. So it's already in there, so we're good. And then we got 2 more meetings, Kona and then at the beginning of 26 to just kind of fix bugs. But at this point, so yeah, there might be minor changes to this feature. This is not like the final standard version of it because the standard isn't out yet. There might be minor changes if we discover any bugs, any defects, but I don't expect any major changes. So this will be in the C++26 standard when it comes out, either in this form or something very, very, very similar to this. So this is good. This is big news. This happened just literally at the last committee meeting like a month ago. And this is the culmination of 21 years of work trying to get this feature into the standard. That's a lot of time. So the first proposal to add contracts to the standard is actually from 2004. So this is how long it took to get this feature into the standard. The first proposal kind of got abandoned. Then you got a second one, which was pioneered by a bunch of people from Bloomberg. It's kind of macro-based. That failed in the committee. And there was a third one, which was this like attribute-like, like with 2 double square brackets. You might have seen that. That was approved for C++20 in 2018, and then in 2019 it was removed again because we turned out that it doesn't quite work. And then we got a study group that was founded in 2019, actually 21, and then that was working for 6 years now on this 4th iteration of this proposal, and finally now it's been approved again. And we are now, in a good spot here after 21 years of work. And why did it take so long? Why did it take 21 years to standardize this feature? Well, there's a lot of reasons. Some of them I'm not going to mention here. You can ask me at the bar later. But I have actually a new theory why. And it has to do with, actually, it's actually not my theory, actually, it's something that I think Alistair Meredith told me recently. But I think he's right. A lot of it has to do with the name. So we call them contract assertions. And there's this word here, contract, and that word comes with a lot of baggage. And I think if we had just named this feature or this proposal assertions, then people would have said, oh yeah, cool. These are just a new, better way of writing assertions. This is clearly useful. Let's standardize it. And you would have finished a long time ago. But because there is this word contract assertions in there, people have a lot more expectations about what that actually means and what it does. And if those expectations then are not quite met in the way that people expect, then there's going to be opposition. There's going to be, oh, maybe you should do it this way instead, and lots of discussions. And then it takes 20 years to agree on the committee. And so what are actually contracts? Not contract assertions, but contracts. This feels like it's kind of an important part of the puzzle here. So in order to answer that, we need to go back to the 80s, which is where this was invented. Design by contract is an approach for software design pioneered by Bertrand Meyer in the 80s. And first implemented in his programming language, Eiffel, in 1986. Later, the D language, which was published in 2001 also had design by contract built in a very, very similar way. And then later still Ada, which had been around for much longer, but in 2012, contract support was added to Ada. And those three languages kind of do it in a particular way, in a kind of similar way, not quite the same, but very similar. And there's other languages that do it differently, and we now in C++26 do it yet differently. But the way it was conceived by Burton Meyer, design by contract is an approach for software design that defines formal, precise, and verifiable interface specifications for software components, such as functions, classes, etc. And by extending their ordinary definition with preconditions, postconditions, and invariants, which come in different flavors, class invariants, loop invariants, etc. And we call those additional interface specification contracts in accordance with the conceptual metaphor with the conditions and obligations of business contracts. So this is particularly clear when you look at preconditions and postconditions. So a precondition is a condition on when you call a function on the parameters you passed in and the kind of the overall program state at that point. And it's the obligation or the contract, the obligation of the person calling that function to make sure that those conditions are met. And then the function implementation can rely on those being met. And then the postcondition is kind of the reverse. It's a condition on what the function returns and what state it leaves the program in when it returns. And that is an obligation of the person who implemented that function to make sure that that holds. And then the caller can rely on those things having been established when the function returns. There's kind of this mutual agreement. And invariants are yet another flavor of that. This is kind of the concept of contracts, and these contracts are actually everywhere today, even without contract assertions. And most often contracts are there in the form of what we call plain language contracts, contracts that are expressed in English or some other human language, like in a code comment. Very often you have a function like this, and then it's like a vector operator square bracket, and it says that you have a bug, and in this case, because it's C++, potentially also undefined behavior, if your index is out of bounds, right? So that's a precondition of that function. That's a contract. So it could be in a code comment. It could be also in a separate document, like the C++ standard itself defines preconditions and has done so since the 90s, right? So C++ had contracts since the 90s, since the beginning. It's a precondition of operator square bracket that is smaller than size. And the standard actually spells out, again, since the 90s, what preconditions and postconditions are, right? The conditions that the function assumes to hold whenever it's called. Violation of any precondition results in undefined behavior. That's a peculiarity of C++. That doesn't always have to be the case. And then postconditions are the conditions that are established by the function, right? So that is contracts, right? So we got them either in a specification or in a code comment. Could be also part of your coding guidelines. It could even be an unwritten contract. For example, if you got a const member function, that's thread safe. That's a contract, which maybe nobody ever wrote down at your company, but people just know that it's there. So that's also part of the contract. In whichever way it's written down or not written down, it's somehow part of the specification of a function or a class or whatever you have. And it's somehow part of what you intended to write when you wrote that code. That's kind of what the contract is. And that's really cool because that gives us a definition for correctness. So we can say that a correct program is a program that does not violate its plain language contract. It doesn't violate what the specification says it should do and what the developers intended that it should do. And often we can't talk about the program always being correct. Probably that is not a thing that exists, but we can talk about correct behavior. So if you execute a particular program, a part of a program with a particular set of inputs, and then what happens next does not violate the plain language contract of that component, then that component of your program has correct behavior. So that's really important. It gives us a definition of correctness, which is kind of hard to nail down if you don't have this concept of contracts. And so that has been around since forever, at least conceptually. And the new thing, and also it's not really new because we had macro assert also since the 80s or something. But what we want to do now in C++ in a way that's better than microassert is you want to express the contract in code, right? Not just in English or implicitly, but in code, and that's exactly what contract assertions are. Now, the problem with this is that there's many, many ways in which you could specify a feature like this, and there's many, many things you could do with it. And I think that's part of the reason why it took 20 years to standardize, because you could take this into many different directions, and different programming languages have taken it into many different directions. So we kind of have to nail down, like, what do we actually want to do for C++? And people have very different opinions on it, right? If you ask 10 members of the C++ committee, what do you think contracts should be doing? You get 11 different answers. So maybe not anymore now, but certainly that was the case a couple of years ago. In fact, when we started SG21 after the C++20 proposal failed in the committee, so we started SG21, the study group, and then the first thing we did, we said, okay, let's throw away all the old work, let's start from scratch, figure out what we're actually doing here. So we started collecting use cases for contracts, right? So if you want to add contract assertions to C++, why? What do we want to do with that? And guess how many use cases we identify? Anybody wants to shout out a number? 3. Anybody more? 30. Okay. 196. Right. So they're you can group them roughly. They're not like all completely different from each other. So, you can make this like word cloud here. Those are all the different things that different people want to use contracts for. And there's quite a lot of stuff, and a lot of it is kind of pulling into different directions and mutually exclusive. And you kind of can't really do all of that at the same time. I mean, you could try to specify something that does all of this at the same time. Then you end up with something like trying to create this mystical being from German folklore, which is the egg-laying wool milk pig. I don't know how well that translates to English, but if any of you are Germans in the room, you know what I'm talking about. So you're trying to do this thing that lays eggs and gives you wool and meat and like milk all at the same time. And that's what we have tried with contracts, and turned out like you can't really specify anything like that. It's way too complex. We're never going to agree on how to do that. So then the next phase we entered after we figured that we can't do that is, okay, we have to limit ourselves to like a subset of those use cases. And then everybody, so this is now a tale from Russian folklore, the swan, the pike, and the crab. So they got something in this cart that they want, some food or something valuable, and they want to bring it home, but everybody pulls into a different direction. So the fish pulls into the water, the crab pulls sideways, and the swan pulls up into the sky, and so the cart never moves, and it's actually still there where it was. And so this is the situation we were in afterwards in the committee, where everybody wanted to get their use case. And if somebody says, oh no, but contract should be doing this other thing, they were saying, no, this is all wrong. I want my use case to be satisfied. And so we spent a few years doing that, which also wasn't particularly productive. And then the reason it took so long is because it took so long to get the committee on board this idea that we just can't satisfy everybody's use case in the first version, but we still need to start somewhere. We have to standardize a first version of this, which satisfies a few use cases, lets you do some stuff that is useful to somebody, and provides a foundation so we can do all the other good stuff later. So that is what we now have in C++26. C++26 contract assertions. That's what the feature is called. They are an MVP, they're a minimal viable product. They don't do everything, they do some of the stuff, but they are a foundation for future evolution. And so agreeing on that was enough to get the proposal past SG21, which was the subgroup on the committee that was doing contracts for the last 6 years. It wasn't quite enough to pass the next stage to get the evolution working group on board, which is the kind of bigger kind of superordinate subgroup on the committee that has to approve the design of all features that go into the standard. So there, in that bigger group, we faced the problem that there were lots of different opinions on, what contract assertions are or are not. So we had to do a lot of work convincing people that, no, that's not what contract assertions are. That's what they are. So let me try and kind of summarize this. At the very basic level, I think it's clear from the description in the beginning of the talk is that contract assertions fundamentally are a tool for finding bugs. Okay, that's what they are. To be more specific, they are a tool for finding bugs during program execution. So you write assertions, and those assertions are evaluated. There's a Boolean expression there that runs, right? It's checked, and then it has a result. It's a runtime thing. That's really important. Well, actually not quite, because program execution also involves constant evaluation, and that actually also works in C++26. So if you have a const expr function, and you put a precondition on a const expr function, and then you call that in some manifestly constant evaluated context, like for example, you call it in order to establish a template argument here, you will get, if the semantic that you chose is enforce, you will get a compile error. When constant evaluation hits that line of code, you will get an error at compile time. But that's still part of program execution. What it is not is a way to constrain or subset the language. That is something that, for example, profiles, a feature that didn't make C++26 that people are working on, is trying to do, among other things, is to say, well, you know, this feature like reinterpret cast, for example, it's unsafe, it could have UB, so we don't let you write that if you enable this option, it's ill-formed, right? And that way you prevent bugs, by subsetting the language or constraining the language. And contracts do not do that. They're not designed to do that. They're not even designed to change the semantics of the language in any way, right? Nothing changes when you enable contracts unless you actually add assertions, and then evaluation actually gets to that assertion and checks it, right? So it's kind of different. It's not a tool to subset the language to like remove unsafe stuff, but it's a tool to find bugs that those static approaches don't find. Like anything that falls through the cracks of like making the language better can then be caught by assertions at runtime. So it's like another layer of safety, so to say. Context assertions are always redundant in a correct program, right? Because they check for correctness, they check that you don't have a bug. So if you don't have a bug, they are doing nothing useful. So that's kind of by definition, they are redundant in a correct program. And the corollary from that is that they are not an error handling mechanism. So that's really, really important. There's a distinction between finding a bug, which is you wrote the wrong code, and handling an error, which could be you got wrong input from somewhere else, but the program you wrote is still correct. So that is not what contracts are for. They're not an error handling mechanism. So you're not supposed to use them for things like input validation. For example, if you have a function that, I don't know, parses a string and like determines what integer that string represents and returns that integer, then it could be an error to pass an empty string, but you should not write that as a precondition assertion, because if you do that and then somebody ignores that precondition assertion, which you can always do, then you hit a bug later here. You get undefined behavior here, right? That's bad. What you want to do is you want to make sure that that function never has undefined behavior, regardless of whether the checks are on or off. And in fact, probably passing in an empty string is not a bug in your program, but something that can just happen normally. So it's actually an error. So you should actually do error handling. You should unconditionally check for this thing and then handle it somehow by throwing an exception or do something else. But that's error handling. That's very, very different from contract checking. So it's very important to distinguish those two things. The other thing that contract assertions are not, they are not unit tests. That's another thing that, particularly when it comes to postconditions, people tend to confuse a little bit. So if you have, for example, a function that computes a square root, and I'm going to gloss over the existence of floating point for a minute here, and just say, okay, you got a square root function, and you just write a bunch of unit tests, right, to make sure it's correct. It's a very good way of checking for correctness, but what you're doing here is you're testing with concrete inputs. That's not what contract assertions are. Contract assertions check on the other side for any input you may receive, right? So you might have, again, glossing over the existence of real numbers and floating point. You might have pre and post conditions like this, and if you turn them on, they will check your function regardless of who calls it where and with what input. Now, actually, it kind of circles back, because something that you really, really want to do is then also write unit tests for those assertions to make sure that they're actually there, right? So you want to have a unit test, something like this. And there's ways to do this, and there's reasons why this is important, not this talk. I have a paper about this. I gave a talk about this together with Pablo Halpern at CPBCon 2023. So go watch that, read that, very important, not for today. Even more important is that contract assertions can only ever express a subset of the actual contract, the plain language contract, because in general, the plain language contract, the actual contract that determines whether your code is correct, you can't express all of that in code normally. Sometimes you can, right? So if you're talking about vector operator square bracket, it has a precondition that is very trivial to express as a precondition assertion, right? It's a Boolean check that you can write. You kind of know, what the computer is going to do if you enable that check. Sometimes it's not that easy. For example, if you have a binary search, you can also write code that checks the precondition that the range is sorted. But the problem is that the algorithm is log n, but the check is on. So checking the contract you can do it, but it will actually break another contract, which is the algorithmic complexity guarantee. So you don't probably want to, in general, do this. And sometimes it's even worse. You cannot even write an expression in C++ that checks the contract. Like, this pointer points to an existing object, right? You need instrumentation to do this. Or something like a borrow checker in Rust, which we don't have in C++. Or this function will return. That's the halting problem. Obviously, you cannot write a Boolean expression that verifies that, but that is still part of the actual contract. So again, contract assertions, right? Contract assertions are just there to check some subset that you can express or choose to express in code. Here's another thing that you cannot do with contract assertions in CSS 26. If you have a function that doesn't have a definition, there's no code you can run. If you try to write a precondition that calls that, you're going to get an error at link time because there is no code to run, right? So we're not talking about symbolic execution here or static analysis or something like this. We're talking about there's a Boolean expression we need to evaluate, right? Otherwise, you can't write it. So contract assertions can only express a subset of the plain language contract. And so they are useful for static analysis, right? So a static analysis tool can look at these assertions and try and figure out what they mean and try to find bugs that way. But sometimes, they won't be something you can, that the static analysis tool can usefully use. And in particular, because it's only a subset, you cannot use contract assertions to prove that your program is correct. And this is something that when people hear contracts, they kind of have this idea that this is what they're for, but they should somehow be used for a formal correctness proof. And there are languages like Daphne, for example. There's a keynote from Parent talking about that, where you kind of can do that, but not in C++. It kind of just doesn't make sense. It's not really feasible to do this in C++. So contract assertions are there to find bugs, but not to prove that your program is correct. That's not really something you can do with code, right? And finally, contract assertions, because you can turn them off or switch them from ignore to enforce or from enforce to quick enforce, they don't guarantee any particular runtime behavior, right? So if you write a precondition assertion like this, what you're expressing is that it is a bug to call this function if that evaluates to false. But what you're not expressing is that that must be checked, or it must terminate the app, if that fails or something like this. You leave this as a configuration option open to the person compiling the code. If you want deterministic behavior, then you would have to write something like an if statement, right? So the thing about contracts is that there can be multiple different behaviors here, right? So we already said that you get one of those 4 evaluation semantics, but when you write that, you don't know which one you're going to get, because if you're writing the code, you're not the person deciding that. The person compiling the program is deciding that, right? So you know you're going to get one of those 4. Some of them terminate the program, and again, there is freedom for the implementation how that happens. So it could terminate, it could abort, it could just terminate, like a trap instruction. All of those have important use cases, so we don't want to say in the standard, always do just this one. And finally, you could have the default contract violation handler or a user-defined contract violation handler, and those handlers could do different things. They could return, which they should normally do, but they could also throw or terminate themselves or do something else, right? So you get all of these different possible runtime behaviors, and this is really the novel thing here. Contract assertions provide this separation. On the one hand, you have the separation into a caller and callee, so a person writing the function and a person using it. And depending on who you are, you either ensure the precondition expects the postcondition or the other way around. So that's kind of a symmetric thing. That's the contract aspect of it. But more importantly, or just as importantly, there's a third person here, which is the person actually compiling the program and choosing what evaluation semantics to use and whether to use a custom contract relation header and what that should do. And those are typically, 3 different people, right? And so you have the separation of concerns. And that is really a new thing. That's not something that existing C++ features until now were really taking into account. But that's what makes this like scalable and applicable to many, many different scenarios. And that's what gets more assertions into more code bases, essentially. So let me drill down a little bit more into this idea that the evaluation semantic can be chosen in any way. It actually, the standard actually doesn't specify, or the C++26 draft doesn't specify in how you choose it, right? So GCC and Clang provide a flag to do it per translation unit, just the way ndebug does it today, but that's not the only option. You can choose it at compile time per TU or for the whole program. It could show you could choose it at load time, at link time, or even at runtime, right? Theoretically, you could have hooks into every assertion, and then at runtime you choose if they're enforced or ignored. And that's also a valid implementation. So you want to enable all of those options, right? And so there's a bunch of papers here again to kind of talking about the different use cases that this enables, which you cannot do with macro assertions today, right? So that's really powerful. It lets you do things like, each contract assertion or each next evaluation of the same contract assertion even can have a different semantic, right? So you could say, I want to check only the pre but not the post conditioned assertion, or I want to check some statistic random. It's too expensive to check all assertions. I just want to check 10% of them, maybe every 10th, or somehow randomly distributed. I just want to do like a stochastic analysis or something. So all of these options are things that C++26 allows. So compilers can offer flags for those things. And another interesting quirk here is somebody asked earlier about whether they're checked on the caller side or on the callee side. So actually, they could be checked on either side, right? And that is interesting because that leads to evaluations that could be repeated. So kind of conceptually, this is what you want, right? You have a caller, you have a callee, and then there's pre and post conditions, and you kind of check them. You check the preconditions, and you call the function, you check the post conditions, you return. But of course, in practice, because it's C++, it looks like this. We have a caller's translation unit and a callee's translation unit. You compile them independently. And so you might compile a callee translation unit with or without checks on, and you might compile a caller's translation unit with or without checks on, and checks could be either on the caller side or on the callee side. We don't really prescribe that in the standard because both of them have important use cases, right? So depending on what your compiler does and what flags it offers you, you could end up in a situation where, both in the caller's translation unit and in the callee's translation unit, those things are checked because they don't know each other. You still want them to be able to link together without knowing whether checks are enabled in the other translation unit, right? So you could end up in a situation where you get all of these checks twice, right? And also, you might want to allow to have them elided. In particular, if the compiler looks at an assertion and it says, okay, well, I know that this is always going to be true or always going to be false, it should be allowed, and it is allowed in C++26, to then not actually perform the check. With the consequence that if you can get the checks once or twice or not at all, and you don't really know, is you can't rely on any side effects of those checks happening. And there was another question, I think, from you there in the back. What happens when your assertions have side effects? That's not something you should normally have, but if you do, you cannot rely on them happening. And so very concretely, if you have, for example, a check function that, I don't know, returns true or false or whatever, and then increments a global counter as a side effect, and then you use that function in a precondition assertion or in a contract assert or in a post, and then you call that function. You don't know what the counter is going to be. Like even if all assertions are enforced, still, you know, this program could return 0 or 1 or 2 or 17. It's probably not going to return 17, but in the standard we just say you can't rely on those side effects happening at all or how many times they're happening. So what this is essentially it's an exception from what we call the as-if rule. It's like copy elision, which you already have, right? If you have a copy constructor and the copy constructor has a side effect, because we have copy elision, you don't know whether those side effects of your copy constructor will happen or how many times they will happen, because the compiler is free to elide the copies, right? And it's kind of the same here. The compiler is free to elide the contract checks if it knows what the result is going to be. And it's also free to check them twice, or maybe even more than twice if you have some kind of very weird scenario with multiple translation units somehow. So yeah, even with all checks enforced, you can't rely on side effects happening any particular number of times. And that has a consequence. It means that it's not quite the same as cassert, where cassert, you know that all the checks are going to be on or off, right? For the entire translation unit at least. So you could do things with cassert like this. This is an example from an actual existing code base. I think from Clang, kind of paraphrased a bit, where they have an assertion that a particular iteration doesn't happen more than max number of times, and they increment this counter inside the assertion. And with cassert you can do it, but with contact assert you can't, because you don't know. Maybe the first time it's going to be ignored, the second time it's going to be enforced, and the third time it's going to be ignored again, right? That's completely allowed. And also it could happen twice, or the compiler could say, well, I kind of know that this is 0 now and max iter is 6 now, and so it cannot be 6. It has to be below 6, so it can actually replace this with contract assert true without incrementing an iter. And so you can't do this. This is not going to reliably work. You have to move the modifying operation out of the assertion and have a side effect free expression in the contract assertion. And that is actually a special case of what we call the prime directive, not the Star Trek prime directive, the contracts prime directive, which is that it's kind of the fundamental design principle of this feature is that the presence or evaluation of a contract assertion in a program should not alter the correctness of that program, okay? So what does that mean concretely? If you're evaluating a contract assertion, then that should not affect any state of the program that you can access outside of that evaluation. So when you add a contract assertion, it should not somehow change the semantics of the program or change what code is executed. It should not affect overload resolution or whether a function is no except. You should not be able to sphere on whether the assertion is there, etc., etc. If you add a contract assertion, you ignore it, it should likewise not actually do anything ever. And if you evaluate a contract assertion, or whether you evaluate a contract assertion, should not change the result of another contract assertion, or maybe a later evaluation of the same assertion. So that this counter example here, the example with the counter, incrementing the counter. Don't do that. Some of those are kind of enforced by the language specification. So we got these rules in place that if you try to sphere on whether an assertion is there, you get a hard error instead. And if you try to like put an assertion somewhere in a way that it changes the no except, like whether a function is no except, you will also find that you can't do that. If you try to, for example, put an assertion into a lambda to trigger a capture, which changes the layout of the closure type, you will realize that that also gives you a compiler error. So we designed this feature in a way that you cannot really add an assertion in a way that changes what the program is going to do, apart from that check. But some of those, like the compiler doesn't really know what to do there. So it's kind of the responsibility of the user in particular to not write assertions that kind of affect state elsewhere in the program. So we don't support contract assertions whose predicates could affect the correctness of the program or like the state of the program somewhere else in a way that affects whether the program is correct. The benefit of that which is great compared to C-assert, is that you cannot get these Heisenbugs where you put an assertion there, or you turn it on, and the bug disappears. You turn it off, the bug is there again. You cannot get that with contract assertions. But the downside is that you cannot just search and replace assert with contract assert, because for assert, side effects might work, and for contract assert, they don't. Now, when I say are not supported, what does that actually mean? So that's actually a complicated question. So, some people expect that, if you write an expression inside an assertion that has a side effect, then that should just not compile, right? That's the default. A bunch of people are nodding. Well, you can't do that because, determining whether an expression has a side effect in C++, that's like halting problem hard. You cannot reasonably determine that for every expression. What you could do is you could say, okay, well, we can't tell whether this contract predicate has a side effect, but you're going to restrict that's kind of the next best thing, and a couple of people are going to be nodding now, I guess, in a second again. You could say, well, you can only write expressions for which we can prove that they don't have side effects, right? And compilers have these things, but turns out if you do that, you end up with such a small set of things you can actually write in an assertion that it's just too small to actually be useful in a real-world code base. So you can't do that either. The third thing we could do is what C++20 contract actually did, which was one of the reasons why they spectacularly failed, is to say side effects in assertions are UB. That is very bad. We don't want to add more UB to the language. You want to remove UB. So you can't do that either. And finally, even if we could do any of those things, turns out side effects in the strict kind of core language sense, they're not all destructive. There are many cases where having a side effect in an assertion is fine. For example, if you have a contract assertion which calls a function, which logs something, that is probably okay. That's not going to affect the correctness of your program, unless it's part of the plain language contract of your program how many lines of text it prints. Then it is a destructive side effect. The compiler doesn't know that, right? Similarly, if you want to check a value in an assertion, and that's accessed by multiple threads at the same time, so you need to maybe take a lock, check it, release the lock, that is probably fine. Maybe it's not if that thread has to be lock-free for whatever reason, because it's a real-time application. The compiler doesn't know that, right? So you cannot ban those things because they're useful, but they can also be destructive. So the only thing we really can do is leave it to the user and say, don't write assertions with side effects unless you really know what you're doing. But we can do a little bit to help you. We have this feature called constification. This is a weird word that somebody came up with. It's great because if you just type that, autocorrect will change that to constipation. Pretty much everywhere. It's a lot of fun. So what constification is that inside a contract assertion predicate, all the variables declared outside of that predicate are implicitly const, in the same way as a class member is implicitly const in a const member function, or a capture is implicitly const in a lambda, same thing. If you try to do this, modify a parameter or a global variable or anything else declared outside of that precondition assertion, it's going to tell you, no, you can't do that, it's const. Right, same in a postcondition. If you try to modify the return value of the function that you're checking the postcondition on, probably a very bad idea. Compiler's not going to let you do that. It's going to say that's const here. Similarly, this is a bug that, with C-assert, happens a lot. It costs a lot of money to fix those things. Somebody doesn't quite understand that you can turn assertions off, and they say, well, they're going to call some modifying operation on the object, and then they're going to assert that that's true, and they're going to do it all in here. And then on your machine, in debug mode, it works great. And then in release, assertions are turned off, and suddenly the modification no longer happens, and the developer is very confused why the code is broken. Happens a lot with C-asserts. We got rid of that problem because C++26 is not going to let you do that. It's going to say, well, .modify is not a const member function. You can't call that here. You can't modify the widget here, right? And inside the assertion. It has an unfortunate side effect is if you're in an unfortunate situation where your API is not const correct, and you have something like widget is valid, which is a member function that genuinely doesn't change anything and is actually fine to check in an assertion, but you forgot to add const, you also get an error here. And like, obviously the correct way to fix this is to make your code const correct and add the const there, but maybe you can't do that because it's a legacy API, can't modify it. So then you have to do this really ugly thing where you have to const cast away the const. And that works. It's not UB because the object isn't actually const, right? So that's not UB or anything, it's just ugly. So yeah, that is constification. It's gonna prevent you from doing things and assertions you're not supposed to do unless you really want to. Here's like a more complete code example. There's a few exceptions to this. One is if you have a variable that's actually declared inside the predicate somehow, like in a nested lambda, which is probably very rare, kind of for completeness sake. If it's definitely not visible anywhere outside of the precondition, then you can modify it. And the other exception is we don't do deep const because that's not really, we don't really know how to do that without breaking a bunch of stuff. So the pointer is const implicitly, but the thing it's pointing to is not. Because in order to make that work, you have to trickle const all the way through all the code everywhere, and like we don't know how to specify that. That's just doesn't work. That's another whole talk, like deep const, big topic, but we can't really do it, unfortunately. So one more gotcha that has to do with const, referring to parameters in postconditions. That's an important one because that's another thing where if you hit this, like you're gonna get a compiler error, so it's not, you can't really mess it up. Like the compiler's gonna tell you don't do that, but you might scratch your head a little bit. So I'm just gonna talk about this very briefly. Kind of my favorite example for this is clamp. Does everybody know what clamp does? Does somebody not know what clamp does? Okay, Daisy doesn't know what clamp does. It takes a value and a min and a max, and it returns the value if it's within that interval, and otherwise it's gonna return min if the value would be smaller, or max if the value would be bigger. So it kind of forces the value within that interval. And that function has a bunch of pre and post conditions that we can express and pre and post conditions assertions. I'm gonna think about that for a second. It's gonna look something like this. And so this looks reasonable, right? Except it's not gonna compile. The compiler is gonna tell you, well, you're referring to a function parameter inside a post condition, but that function parameter is not const, you can't do that. That's weird, right? That's confusing. Like, since when do we declare by value parameters const? Like, we don't really, like, it doesn't really matter, right? Like, it's still the same function. Like in C++, you don't really do that unless as an implementation detail or something. So that's new and weird, but it turns out it has to be that way because if we didn't have this compiler error, you could implement clamp like this, which is a completely broken implementation that just sets everything to 0 and returns 0, but all the pre and post conditions would pass, right? If you look at that code, the post conditions pass. Everything's 0, everything's true. So it turns out if you modify the parameters in the implementation, because the post condition assertions are on the declaration, they don't know about the body of the function. So, but the post conditions are checked when the function returns. So post conditions only make any sense to anybody if you can reason about those parameters not having been modified inside the function. Otherwise, the post conditions are meaningless because you have no idea what values they're actually talking about. So you need to force any parameter that is being referred to in the post condition to not actually change before that post condition is checked. So you have to declare those consts in order to use them in a post condition assertions like that. And that's kind of weird, because until now we didn't have to do this in C++, but it's something that we kind of have to accept if we don't want to have broken post conditions. So now if you do this, you're going to get a compiler error because you can't modify them, but if you implement it correctly, everything is okay. There's a question?
So the const for the parameters in C++ is not part of the function signature?
It is not part of the function signature, correct.
So it's still not part of the function signature, but in this context?
Yes,
okay.
Like the const is not going to change the function signature, or the function type, or break, or like affect anything outside of that in any way. But you have to put it there in order to write those post conditions. as a safeguard to make sure that you actually know what parameters you're talking about. That has another interesting side effect when it comes to putting postconditions on coroutines. And you might think, oh, well, that's kind of very weird. Like well, how would that even work? Because a function returns once, a coroutine suspends and resumes multiple times. What does a postcondition even mean on a coroutine? That's very confusing. Turns out it's actually not as confusing at all, because whether a function is a coroutine is actually an implementation detail, and the caller doesn't actually know about this. If you call a function, all of this coroutine magic is happening afterwards, like once you get the object back and then you work with that. But like when you just call the function, it's just a normal function, right? It's called this ramp function, which is then creating the coroutine frame, blah, 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 blah. Turns out pre and post condition is kind of on this ramp function, which is just a function, so it's fine. You can put pre and post on coroutine, but if you try to then mention a parameter name in there, even if it's const, turns out if you then make that function a coroutine, you get an error. That function can't be implemented as a coroutine because you're referring to a parameter in post, even if it's const. And turns out, if you dig into the standard, coroutines are, the way coroutines are specified in CSS is super, super, super weird. And so it turns out that if you have a parameter in the coroutine and you declare it const, it's not actually const. And the reason it's not actually const is because like the parameter that you refer to in the coroutine body is not actually the parameter you passed in. It's a copy of the parameter, which is, the standard says, direct initialized from an x value of type t referring to the parameter, which in English means it's moving from the parameter. Even if it's const, it's still moving from it, which is like super weird. But until now, it wasn't even observable. But if you stick a post condition there, that obviously refers to the original parameter object, because that's the only one that is known at the call site. So then that becomes observable. So if you have this parameter limit and you refer to it in the body of a coroutine, that's not actually the original parameter object. It's a copy that has been moved to from the original one. And if it's an int, unobservable, move, copy, it's all the same. But if you have a big int, maybe a non-trivial type that has some dynamic stuff on the heap, you will see that this one in the post condition there is actually a moved from value. So the post condition, again, will not do what you think it does. So actually, you cannot refer to parameters and post conditions at all if the function is a coroutine, because there's no way for a coroutine to make sure that the parameter will never get modified, because it always will, because that's how coroutines work. Okay, confusing. I don't think many people will do this. Post conditions on coroutines is kind of more of an edge casey thing. There's one more thing I want to mention. ODR. So with CAssert, everything is quite sad. Let's say you have a function in a header, and there is a CAssert assertion macro in there. Now you include that header in one translation unit, you compile it with checks off. Because either you know that it's correct, or you don't care, you care about speed in this translation unit more than you care about correctness. Then you have another translation unit where there's another function that also calls foo, and that one is compiled with checks on. Maybe that's a safety critical one. It's really important that the checks are happening, and if you call it wrong, like here, you terminate and you don't continue, right? And now you have a third translation unit where you call that buzz function there, and that also has the checks on. So will that assertion there actually get checked if you call it from main? What happens here? Anybody?
Nobody knows.
Nobody knows. It's an ODR violation because you have two different definitions of foo in the same program. So the linker will just choose one, or it's an ODR violation, so it's like UB essentially, except at link time. So anything can happen really. Like you can have a dragon emerging from your computer and setting your room on fire, and that is actually conforming behavior according to the C++ standard. So ODR violations are not great. We fixed it with contract assertions. That's not an ODR violation, not a macro. So you can compile this with ignore and the other one with enforce, and it's still the same definition, right? It's token by token, the same definition, which is how the standard defines ODR. So it's not an ODR violation if you do this. However, you still have different code generated here, right? So in TU1, you get a version without the check, and in TU2 you get a version with the check. So you still have two different versions of the same function with different code gen in the same program. So it's technically not an ODR violation, but you still kind of have the same problem. What happens? So you can't get the dragon. That's good, we fixed that. But you still can get either definition, right? So how do we go about this? And it turns out there's three properties that we kind of want. One is you want to be reasoned about what version gets chosen. Like, do you get the checks or do you not get the checks? That's a red blob. You want to be compatible with today's linkers and ABIs, and we want to not have runtime overhead when you turn the checks off. And it turns out, because of the way C++ works and linkers work, and this is not a property of this proposal, but that's just a property of the universe, you can only ever get two of those, but not all three at the same time. The good news is you can choose. So currently, GCC and Clang they choose these two. So this is kind of the same behavior you in practice get with C assert today. They just choose one of the implementations at random. You don't know which one. So you don't get deterministic choice of semantic. You don't actually know whether the checks are going to happen or not. But you don't break the ABI, and you still don't have runtime overhead if you ignore them. Another possible choice would be to say, well, we can expose the contract assertion evaluation semantic in the ABI somehow. And then the linker can pick it up and say, OK, here's the version with checks. Here's the version without checks. This translation unit says they want checks, so we're going to pick this one. So then you choose these two. But that means you need to have smarter linkers that do new stuff. So that would force everybody to update their linker. We cannot do that, right? So we can do that as an option, but we cannot force the entire community to do this. So you could choose this, or you could choose those two, which is what Herb Sutter has done in his CPP2 implementation of contracts, where he inserts a little runtime hook into every single assertion, and then you get to choose deterministically the semantic at the end during runtime, essentially. And then you get those two properties, but you still get this. There's no way to not have runtime overhead because you have this hook, even if it's ignored. So choose two. I guess compilers will eventually offer you all possible options, and you can choose the correct one for your use case. And here's one more topic I want to talk about, since I have a little bit more time.
Timur.
Yeah, there was a question.
Yeah, so on that last slide, is it safe to say that this is a problem that we could talk about at the dependency management level, and which is outside the scope of ISO, which is the scope of your talk, right? But
yeah, I don't want to talk about this for the next 20 minutes because I have
I don't want to talk about it either, but to say it's impossible is a little overstating. It's just saying using the tools in our toolbox right now, we don't have an ISO paper to write to describe that.
We don't know how to get all three at the same time right now. I don't believe it's possible, but you might be able to convince me otherwise.
I don't think it's possible with an ISO paper.
All right, let's have a conversation afterwards. All right, let's move on. Are contract assertions safe? That's another thing that delayed standardization of this feature by a couple of years because people were saying, now it's all about safety. Like we don't want to standardize a feature if it's not safe. And by safe, usually the last couple of years when we were talking about this on the CPLUS committee, people usually meant we don't want UB, we want to get rid of UB. And so turns out contract assertions don't actually provide a guarantee that you don't have UB, right? So this has tripped a few people up. So let's say you have this operate a square bracket here, and it indexes into a raw array. And obviously, if you then access that out of bounds, you get UB. That's kind of where we are today. If you then stick a precondition assertion on there, that's great if you turn the checks on, right? It's going to hit that assertion. You're going to know you have a bug. But you can also ignore them. And that's kind of the whole point of the feature, right? That you can ignore them if you choose to. So this may still be UB depending on how you compile the program. That was a problem for a bunch of people on the committee. Although, and they were saying, well, you have to essentially force this to always be enforced, which makes the whole feature undeployable. As I said, that you need this observe and ignore mode in order to actually use this in practice at scale. So that was one problem. Another problem is that contract assertions themselves can have UB. Right? So imagine a function that adds two integers, and then you use that function somehow in a precondition assertion. Signed integer overflow is UB, so the compiler can assume that it never happens. So it can assume that f always returns a bigger number than the one you passed in, so it can reason about pre always being true and actually just replace this with pre-true and remove this whole thing entirely, even if it's enforced, because UB can never happen and the compiler can optimize on the assumption that it never can. So are context assertions not safe because of this? Like people were saying, oh, you have to find a way to fix this. Well, this is just how the language works. If you have a way to change the language in a way that evaluating Boolean expressions can never have UB, please tell us how to do that, because we don't know. So that was kind of a source of misunderstandings for a while, and kind of it all bumps against this problem of what is actually safe. What do we actually mean with the word when we say safety? And I wrote this paper about it, P3500, which you can read. It goes into a lot more detail. But basically, the problem is that people are saying safe when we talk about C++, and they mean very, very different things. So they talk past each other all the time. And that's kind of what's been happening here. And I suggest that we stop doing this. We just don't say safe this, safe that, save that. We actually say what we mean. There's very, very different concepts that have almost nothing to do with each other, which is language safety, functional safety, and security. They're very different things. So language safety is the thing that C++ people the last couple of years meant when they said safe, which is basically the code does not have unbounded UB when you execute it. And all of these other safeties like memory safety, thread safety, type safety, initialization safety, all of that stuff, that's like a subset of this language safety, right? Like your code doesn't have UB, right? That is a deterministic property that compilers and tools can reason about, and we can change the language specification in a way that we know that we don't have that anymore. Maybe not with C++ the way it is, but like Rust did that, right? And then on the other hand, you have these other two, functional safety, which is what everybody else outside of C++ means when they say safe, which is essentially this thing is not going to harm you. It's not going to hurt anybody. It's not going to damage humans or property or the environment. It's safe, right? That's functional safety. And then there's also security, which is enabling software to protect its assets from malicious attackers. So it's kind of like stuff that goes wrong in the universe versus a malicious attacker trying to break your thing. And those two are very, very different from language safety, right? They're not deterministic properties. Like something is not safe or unsafe. It can only be more or less safe. It's a statistical property. Determining whether something's safe or not, at least in software and hardware and engineering, usually is regulated somehow by government agencies or something like this. And only humans can really tell, or determine whether something is functionally safe. Like the computer doesn't know that, right? So contracts are really not a tool for this. They don't change the rules of the language. They don't remove UB from the language, but they do let you express criteria on something being like expectations on your program that only the human knows. The compiler doesn't know that if this is false, you have a bug, but you do, so you can write the contract assertion and add it there. So contracts are very much a safety feature, but they're targeting functional safety. They're not targeting language safety so much, and that's kind of the disconnect that we had for a while. So I suggest we kind of use those terms properly. And actually, it's a little bit of a deeper topic. So we have language safety, functional safety, security, and then we have this intersection here. And this is really kind of what contracts are targeting. This is correctness, right? If code is correct, then it has all of these properties. It doesn't have UB, it's functionally safe, it's secure, and contracts are a way to express criteria on when your program is correct. So that's a very deep topic. That's going to be a whole talk on its own. I will actually attempt to give this talk. I have a keynote at this other wonderful conference, CPP on C, coming up in June. And so I will be talking in a lot more depth about that kind of correctness, safety, security stuff, and how contracts fit in there. Now I'm going to kind of wrap this up. The last section I have here is, what do we do next? Where do we go from here? So C++ 29. So we got this in C++ 26. Where do we go in C++ 29 and beyond? There's actually a bunch of stuff we want to do, kind of ordered by how far we are already with this. These are the things that we kind of know we want to add. The kind of thing that is the furthest advanced right now is this one, which is this paper P3400, which Joshua Byrne is working on. which basically solves this problem of, well, you don't really know if this is going to get checked, right? So people say this is not language safe. You need to have a guarantee that you will never be able to move past that code if it fails and into the code with a bug. So we need a way to basically say this, right? To say this one needs to be always enforced, right? So you can do this today with an if statement, but then you can't hook into the contract violation handler and all that good stuff. So this is going to give you that. Of course, it's not just this, right? There's a whole framework that lets you also express never enforce or ignore unless this is true, or only check this in super debug mode where you don't care about the algorithmic complexity of your functions and all of those things, right? So there's a whole framework where you can basically specify little types that like map different semantics and tell the compiler which ones are allowed, and then you use that almost like a template parameter essentially here. So we will add that hopefully early in the C++29 cycle. That's going to alleviate a bunch of kind of concerns, let's say, or satisfy even more use cases than the feature does today. The next one is implicit context assertions. That is my favorite. That's something I'm working on as we speak. This is paper P3100, and that's kind of how we want to tackle this problem. So, it was suggested, well, just don't let you write an expression that has UB. Well, we don't know how to do that. But what we can do is we can say, well, we know what happens here. This is a core language integer addition. It's like something like a built-in addition operator for integer. But we can pretend that that built-in operator that doesn't really exist in code had these precondition assertions, right? Which are checking for signed integer overflow. And then we can pretend that those precondition assertions are there, and then we can actually give you a flag to enable those and to actually inject those checks implicitly into your code, right? Even if you did write this, just by default. So that's pre and post condition assertions on core language stuff. And then we can, give you that flag, and if you turn it on, this will fail if you get it wrong, and it will not have UB anymore. And we can do this for all the UB in the language that you cannot basically check at compile time, but you have to defer to runtime. Because this one, you cannot do anything at compile time about this. You don't know what the value of A is going to be. So for all the UB that you can get rid of at compile time, yes, we should change the language specification to make it safer to remove unsafe stuff. Profiles are one way of doing this. There's other ideas, like we can think about a borrow checker. This is all compile time stuff. But there's always going to be UB that you cannot get rid of at compile time. Like here, you have to do it at runtime. This is the way to do it. Let's do this across the entire language. So very exciting. Hopefully I'm going to give a talk about that next year. Okay, I got a few more minutes. The next one that I'm really excited about, and I'm also working on together with a couple other people, is one missing thing. So think about for a moment the postconditions of pushback. So it got at least 2 you can express in code directly. That the last item is the one you inserted, and the size is 1 more than it was before. Except that with C++26, you just cannot write this, right? Like, how do you refer to the size of the vector it had before you called the function if the postcondition is checked after the function returns? So the feature that we want to add here for C++29 is, I think it's pretty elegant. It's like a lambda capture. You can just capture the value of the parameter when the function is called, and then you can refer to that when the function returns. And that solves another problem, which is this really annoying thing here. Once you have that, you don't have to put const on there anymore. You can just capture the parameter. You can say, I'm capturing by value, and so I'm referring to the parameter value before the function was called, right? Or at the moment the function was called. And then the compiler might have to do a copy for that, but you opt into that, so you're happy to pay for the copy. Or you can capture by reference, and then you're saying, okay, I don't care if the parameter was modified inside the function body. I still want to refer to that original object. So you capture it by reference instead, right? But you can explicitly choose what you want. And that gets rid of this need to put slap const on there. So that's going to be great. The next one is pre and post on virtual functions. This is a really painful concession we had to make to get contracts in the CS26. We had to remove support for pre and post on virtual functions. If you put pre and post on virtual functions, Today it's ill-formed. That's very unfortunate. So in D and Eiffel and Ada, you can do this, and the way it works is if you put pre and post on a base class function and then you override it, then you just implicitly inherit those, and then there's a bit of stuff around. You can widen the preconditions and narrow the postconditions, but not the other way around, which is kind of the classic 80s stuff that Bertrand and Meyer came up with. Turns out Bertrand was kind of wrong. This works well with a language that just does by-the-book object-oriented programming, but as soon as you do more interesting stuff with multiple inheritance or type erasure or all the messed up stuff you can do with C++, this model completely falls apart, and there's lots of use cases that it just doesn't support. So we removed it, and then people were saying, well, we have to support pre and post and virtual functions somehow, so we added back a different model, which is kind of this Kohler-Collie model. It goes back to that. We said, okay, so we check the pre and post on the statically called function, and then also on the function actually selected in this order. And then last summer at the committee meeting in St. Louis, everybody said, oh, this is great. This is a great model. It covers all the use cases. They voted it in. And then at the last meeting, it turns out people are not happy with that. It's a new model. It's apparently scary because it's new. It's not what Bertrand did in the 80s. So it's obviously wrong because that's not what they did in the 80s. So there was a bit of discussion. People were not ready to standardize it this way. So in order to save the rest of the feature, we had to actually remove this entire support for virtual functions. And we have to kind of go back to the drawing board on this. I'm pretty sure we're going to end up exactly with this again. But we just have to do a little bit more work to convince the rest of the committee that that's the correct model. Pre and post and function pointers, another thing that unfortunately we don't support in 2026. Very common, especially for low-level code, is to have, APIs like this, where you have like some function pointer, and then there's kind of they're everywhere in your interface. And it would be really nice to put pre and post conditions on those function pointers, that whenever you call a function through that pointer, this precondition is going to get checked. That, for example, the pointer to the device is not null, and the other two integers are like not negative or whatever. I mean, they're unsigned, but I don't know, that they're not zero, whatever. This is a contrived example, but like it would be very useful to check these things on pointers. Unfortunately, it's really, 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 really hard to do. We had like at least 3 papers that were trying to make this work, and we're kind of just not there yet. Like if you think it through, pre and post on a pointer, kind of that information has to live somewhere. Do you make it part of the type? Do you make it part of the value of the pointer? Do you make it neither? In each case, a bunch of stuff breaks. You can't really do it. Have to come up with some other thing, which is not function pointers, but something similar. That's complicated. We're still working on it. Procedural function interfaces, great thing. That's something that Lisa Lippincott came up with and is working on, which is that you can check pre and post conditions in other scenarios than a function is called and a function returns by value. For example, you could have a contact assertion on what happens when a function throws, and you could assert that it doesn't throw or that it throws a particular exception or whatever, which is not something you can do today with C++26 contracts, but maybe with something like this syntax, you can do very, very, very interesting things, very powerful. Obviously, class invariants, D, Eiffel, and Ada all support them. People want them. They're very hard to get right. So do you check? So it's like a class invariant is basically a precondition and a postcondition every member function. But what happens if you got a private one? What happens if a public one calls a private one, if they call each other recursively? Like, do you, like, it's a bit messy. Like, we don't really know how to get that right. Last one is the assume semantics. So I was talking about 4 evaluation semantics. Actually, there are 5. There is this one, which is like ignore, but actually the compiler assumes that the predicate is true and optimizes on that assumption, which gets you faster code gen in many cases, which is great for performance, great for low latency and real-time stuff. But also, if you mess it up, it adds more UB to the language. So this is not something that we thought was wise to include in the first version of this feature, because otherwise in the current political climate, it would probably have sunk the entire thing. So the need for this is not going away. We know we need this, but we're going to do this later. So I'm actually done now. I got a couple summary slides. Why contract assertions for C++ are great. We got a standard syntax for assertions now, which you can use across all IDEs and tools and platforms and compilers, and everybody agrees on what the syntax is. We can do assertions without macros, which gets rid of a bunch of problems. And we have a much more flexible system for selecting the evaluation semantics, which makes it a lot more scalable, enables lots of more use cases. We have pre- and post-condition assertions on declarations, so you don't have to look into the function implementation to see them. That is extremely powerful for readers, IDEs, compilers, static analysis tools. You can refer directly to the return object, again, something you can't do today without this feature. You get a global contract violation handler. Again, you can't do that today. You can't get Heisenbugs with this design because we have this prime directive thing. And it's designed to be extendable. As you saw in CSS 29, you're going to make it even better. So that's all I have. I have 10 seconds left, so this is my very, very last slide. Related material, I have a blog post where I explained contracts in 5 minutes. So this is a much shorter version of this, which you can share with your colleagues or something. There is P2100, which is the actual proposal, the paper, which has an English description of the entire design and also the wording. Then there's, if you want to dig even deeper, there's P2899, which explains for every design choice why we did that and not something else, and what other people did in the past and why it doesn't work, and references to hundreds of papers where people explored alternatives. And then you can also look into those papers. Like P2899 has, I think it's like 15 pages of bibliography or something like this. There's a wonderful talk by Lisa Lippincott, which explains this whole thing from a very different perspective. Really helps with understanding what this is about. We had this panel at cplusplus London, which kind of talks a little bit about how contracts fit into this bigger picture of safety. And then the last thing I want to highlight is John Lakos' talk, which is going to be happening later this week here at this conference, about kind of also this bigger picture of how contracts fit into safety and security, but also what else we need to do in the future to really make C++ safe and to actually get rid of undefined behavior as well, and what other things we need apart from contracts to get there. And that is now really all I have. Thank you very much for listening.